Hope everyone had a great lunch. It's 1:20, so we're going to get started here with our next session. Our afternoon session today is Atmosphere and Ocean Drivers, number 2. And then myself and colleagues will be convening. I'm Meghan Sharp. I'm a PhD student at Oregon State University.
I'm Emma Robertson. I'm currently a student at Penn State.
I'm Jamin Greenbaum, assistant researcher at the Scripps Institution of Oceanography.
Awesome. Okay, I think, we've kind of gone over the guidelines a few times, so I think we'll just jump into things here. Just a reminder, if you get a yellow square from Emma, that means you have 2 minutes left, so that's your 8-minute mark, and then the red square means that you're at 10 minutes. And then we'll start standing up and walking over towards you if you're 10 plus. So our first speaker of the day is Sophia Pinter, who will be talking to us about accelerated Antarctic ice loss through ocean force changes in subglacial hydrology. Awesome. Take it away.
Hi, can you hear me okay? Great, okay. First of all, thank you for having me. My name is Sophia Pinter, and I'm a first-year PhD student at the University. I'll be talking about here at Cruz about using the subglacial precipitate archive to document changes in subglacial hydrology and ice dynamics and their response to climate. So first off, I just wanted to give some background about what we know about modern subglacial hydrology. So we know that there's an active subglacial hydrologic system beneath the ice, beneath the East Antarctic ice sheet, and there are systems of lakes and channels flowing throughout the base of the ice. These lakes systems are known to flush periodically, and this has been observed using satellite altimetry, which you can see in the image on the left. So the timing and magnitude of this subglacial lake flushing is controlled by hydraulic potential, which is mainly set by steepness of ice with some sensitivity to ice thickness and meltwater input. So what that gives us is larger, more stable lakes closer to the interior of the ice sheet with smaller and less stable lakes closer to the margins. So these systems have been studied over the last few decades, but we wanted to access the subglacial hydrologic record through deep time. And so we're going to do that by looking at these subglacial calcite precipitates, which were provided by the Polar Rock Repository. So these calcite precipitates formed in water bodies underneath the ice sheet up glacier, and they formed in water bodies underneath the ice sheet in or with input from the known subglacial lakes, which you can see on this map. These samples were eventually entrained in basal ice along with other subglacial material and eventually brought to the superglacial moraine known as Reckling Moraine, which is signified by the red star. So how can we construct records of subglacial hydrology using these subglacial precipitates? So you can see that these are finely laminated accumulations of calcite, and we can use uranium-thorium geochronology on multiple horizons of these samples to create an absolute time record of precipitate formation. We can also use physical aspects like grain size and grain volume to indicate subglacial water velocity and get a history of that subglacial hydrology. And lastly, since calcite reflects the chemistry of the water it precipitates out of, we can use the geochemical and isotopic data to record water provenance over time. So just to give you a little picture about what these samples are made of. Like I said before, they're very finely laminated layers of calcite, and on the left you can see that there are detritus-rich calcite layers with the brighter blue layers, and then pure calcite or detritus-poor calcite, which you can see in the darker layers. And lastly, there's detrital silt to sand-sized grains occurring throughout these samples, which you can see by the bright blue grains. So to gain a clearer picture about the environment that these samples formed in, we studied these in thin section. So here you can see some nice photomicrographs of these samples where there are erosional surfaces, well-rounded and well-sorted clasts, and structures indicating unidirectional flow. So this indicates that these samples formed in a water body with intermittent flow. And so therefore, we can interpret that each sedimentary layer is formed by a subglacial flushing event that brings water and sediment into the sample-forming water body. So this gives us a nice record of subglacial hydrology changes. So like I said before, we're interested in how these subglacial water bodies evolve over time. So we used uranium-thorium dating methods to create stratigraphic age models of each of these samples, which you can see here. So we know that precipitation occurred over about 10,000 years during MIS 5. And because these samples have overlapping accumulation times, or formation times, I should say, and they are compositionally and texturally similar, we can link their stories together. So remember I said before that each calcite layer represents a flushing event, or a lake flushing event. So we used the thin section of these samples. You can see all these nice calcite layers where brightness indicates the amount of sediment volume within the calcite layers. So we took a raw spectra and we performed a Fourier transform analysis on the raw spectra. So what we see is that there are two dominant frequencies occurring within the spectra. In order to tell what this actually means from the sample, we use a deconstructed spectra, which you can see from the blue and red curves. So the centennial signal that we're seeing is associated with those fine laminations of calcite. And let me remind you that those are related to flushing events, or caused by flushing events. And then the millennial scale signal is associated with total sediment volume, which you can see in these packets. In these like packets of calcite layers. So we also wanted to look at how lake flushing evolves over time. So the top curve is sorry, this thing vibrates. The top curve is the climate record, EDC temperature record during the time of our study. And you can see that there are these two Antarctic ice topic maxima that are occurring during the period of this study. So Antarctic ice topic maxima, or AIMS, which I'll refer them to as, are associated with Southern Ocean warm periods. So taking you through this figure, the gray curve is the same spectra I showed you in the previous slide, but this time it's in the time domain. So we wanted to look at how that centennial flushing evolves over time. So the blue curve is the relative power of the centennial frequency. So 0 being not periodic and higher values meaning more periodic. So you can see that there are these times where the centennial signal is more periodic, and that coincides with these AIM warm periods. And then lastly, there's also greater sediment volume and larger grain size, indicated by the green curve, occurring during these warm periods. So bringing that back to the physical environment that we're looking at, lake flushing is most periodic during Antarctic ice topic maxima. And during these warm periods, water energy also increases, bringing in those larger sand-sized grains into the sample-forming water body. So lastly, we also looked at how the geochemical composition evolves through time, and also with regard to climate. So I'm not going to go into the specifics about what these isotopic values means, but I'll just say that during those warm periods, we have a uranium concentration and isotopic composition that's higher and also more variable. And so what we can say from this is that during warm periods, waters from more interior regions of the Antarctic ice sheet are brought into the sample-forming water body. So this indicates greater hydrologic connectivity below the ice during these times. So finally, on the right, you can see this diagram. That this is just giving us, or this is what we think is happening during these two different time periods. So during the cold period, we've got a subglacial system that is more isolated and flowing less. And then during the warm period, we've got ocean warming and then greater hydrologic connectivity accessing those interior East Antarctic ice sheet waters. And also during this time, subglacial lake flushing becomes frequent and episodic, and water velocity or water energy of those flushing events also increases. And so I just wanted to point out that in the modern, we've observed that ice velocity increases in ice velocity have been associated with subglacial flushing events. So based on this observation and our data, there's an apparent feedback between ocean warming, ice velocity, and subglacial hydrologic connectivity. Thank you.
Awesome, thank you so much. Our next speaker is not present with us physically today because they are sick, but have recorded their talks. So this will be a talk about ice-penetrating radar evidence for widespread seawater infiltration in West Antarctic ice shelves by Riley Culberg.
Hi everyone, really sorry that we couldn't make it in person, but don't want to get anyone else sick. So a lot of thanks to the organizers for letting me share this work via recording. So I'm going to talk today a bit about some really cool ice-penetrating radar evidence for seawater infiltration in ice shelves that I've been working on with my colleagues, JZ Miller and Ted Scambos. So we've known for decades that it's possible for seawater to infiltrate into permeable firn on ice shelves when pore close-off occurs below sea level. So it might be either because the accumulation on the shelf is high or because the ice shelf itself is very thin. This is a very well documented process on the McMurdo ice shelf, both with cores and with ice-penetrating radar. And there are a few other locations with documented brine. Those are shown in the black dots for cores and the black stars for radar surveys in the map on the right. But there's some additional firn modeling work that was led by Sue Cook that has shown that large swaths of many ice shelves theoretically have large regions where pore close-off is below sea level. So those results are shown in red, yellow, and blue on the map. In particular, I want to point out the red regions, which is areas where the firn density at sea level is modeled to be less than 750 kilograms per meter cubed. So that suggests it should be permeable even by the most conservative standards we have. So you can see there's this really big delta between the modeled plausible extent of seawater infiltration and the observed extent, just due to the sparsity of the observations we have. Now, if seawater infiltration is truly as extensive as the Cook paper suggests, then we should care about these systems for a number of reasons. So first, refreezing of the seawater component, the freshwater component, the seawater, is going to warm the ice shelf and intrude salts into the ice matrix, and that's potentially altering our ice rheology. Second, like firn aquifers, these brine layers might be a perennial source of liquid water that could aid hydrofracture. In fact, that was one of the major hypotheses for disintegration events on the Wilkins ice shelf before we determined that it was hosting a freshwater aquifer instead. And so along that same train of thought, we also think it's possible that brine layers might prime high accumulation ice shelves for freshwater firn aquifer formation, which is going to fill up deep pore space and aid in warming the firn through latent heating. And then, of course, accounting for some kind of loading from dense seawater might be an important impact that we need to think about when we're doing altimetry estimates of ice thickness or basal melt rates. right? But at the end of the day, none of this really matters that much if seawater infiltration is a rare or localized phenomenon. So the first order question that I want to address today is just looking at the true extent of brine layers in West Antarctic ice shelves and thinking a bit about how some of that infiltration might be occurring. So we'll of course turn to my favorite data source, the Operation Icebridge airborne radar surveys. Now there's been a lot of ground-based radar work done in the McMurdo brine zone, like the image that you're seeing there in the upper left from Seth Kimball's paper. And that's shown that brine layers are characterized by an extremely bright reflection of the water table and very high radar attenuation, as you might expect with the salinity. So we're getting enough attenuation that we don't even see a specular ice-water interface underneath the brine. So we can look for those exact same signatures in the airborne data to map brine layers, the rest of West Antarctica with OIB. Now, as an aside, I will mention that you might note that these are kind of the same signatures we use to identify freshwater fern aquifers. In fact, we've compared the Wilkins fern aquifer radar signatures to the McMurdo brine zone signatures. We think there are actually some distinguishing characteristics here. Brine layers seem to lead to more attenuation due to the salinity, and more abrupt or peakier reflections of the water table. So that's some ongoing work that we have to kind of quantify those signatures, find ways to better filter the detections of putative brine that I'll show you later in this talk. So let's go ahead and jump into it. These are preliminary results for West Antarctica. Everywhere that you see a purple line is where we have a brine detection along the flight line. So we find really extensive infiltration on the southern Larsen C and Larsen D, Nickerson, Abbott, and Stange ice shelves, and then there's smaller regions of infiltration near the calving fronts on the Grenoble and George VI. I do want to note that we haven't looked fully at the data over Pine Island, Thwaites, and Cross and Dodson yet, so it's kind of a gap in the map at the moment. Now, on the left, I've zoomed in on those ice shelves, again, showing you our brine detections in purple, and then the claw extent from the bottle. Particularly, we find that almost all of our detections are restricted to regions where the density at sea level is modeled to be less than 750 kilograms per meter cubed. So that's quite consistent with some of the recent work that shows that water flow in fern seems to be pretty severely impeded at higher densities than that. You can see this quantified a little bit better in that bar chart in the center there, where it's showing that of the flight kilometers that cross regions where the fern density is less than 750 kilograms per meter cubed, about 30% of that has brine infiltration, and those detections drop to 5% or less once your density at sea levels would exceed 750 kilograms per meter cubed. So it's kind of the first question answered, yes, we do see extensive seawater infiltration across West Antarctic ice shelves. But having this initial catalog lets us also start to think about how that seawater might be getting into the ice shelves. And so the first mechanism that we see here is one that we've known about since brine was first observed on McMurdo. Seawater seems to infiltrate through porous fern at the calving front, and as long as it can flow back into the ice shelf faster than we lose ice to calving, you get a relatively stable brine layer that's visible in these radiograms. So you can see some modeling examples of this from the Abbott and Nickerson ice shelves in those radiograms on the bottom. We've also observed a couple of new infiltration mechanisms. So one is what appears to be infiltration through the tips or sidewalls of deep basal crevasses or rifts that actually penetrate into the fern layer. So that arrow labeled A in the upper left radiogram is showing kind of a quintessential example of this signature, where we see deflection of the ice shelf surface over the inferred fracture, and then that little cap of brine that flows down and away from the inferred fracture tip. The motive surface image in the upper center is showing you that linear surface feature that we infer to be evidence of the basal fracture a little bit more clearly. Those bottom two radiograms show a few more examples of this mechanism. Each of those white arrows is pointing to that particular combination of surface depression and localized brine cap that were interpreted as water infiltration through the tip of the basal crevasse. We also see a lot of infiltration that seems to occur through thin or damaged ice in the lee of ice rises or near grounding lines. So that upper right-hand radiogram is a really good example of one such brine layer, and the left image is showing you kind of the surface elevation context in this region from REMA. And you can see that that brine layer is one of just a whole series that track this long band of very thin ice near this sort of string of ice rises along the Abbott ice shelf. The bottom right radiogram shows you an example of a brine layer near the grounding line on the southern Abbott that is similarly formed in sort of thin, rumpled ice layer. But one of the, I would say, truly interesting things about these types of brine layers that form in the lee of ice rises or along the grounding line is that they allow seawater to infiltrate kind of into the middle of relatively slow-flowing ice shelves where we don't have calving limiting the extent of infiltration. And so what we see in some of these areas, and these are just a couple of examples, are places where brine terraces are actually visible throughout the entire ice column, not just in the fern. So these are places where seawater has infiltrated near the grounding line, then been incorporated into the body of the shelf as the ice is sort of infected out onto the shelf and burial by new accumulation. And so something like this actually records a very long history of stable infiltration in the same area, all of which suggests that brine is not inherently destabilizing in and of itself. So just to kind of wrap up what we've seen here, we've used airborne ice penetrating radar to show that seawater infiltration is pretty widespread in West Antarctic ice shelves. And most of the infiltration we're seeing seems to occur either through inflow of the calving front, infiltration from the tips of deep basal crevasses, or infiltration through thin or damaged ice near grounding lines or in the lee of ice rises. And this tends to suggest that most seawater infiltration is happening in regions that are in some way already vulnerable to fracture, which would encourage us to think more about the relationships that may exist between brine layer formation, ice rheology, and hydrofracture. But I think it's not at all clear that this is a destabilizing relationship. We certainly see evidence of long-term stable brine layers in some of these slow-flowing areas. And so I think mostly what we've learned is that there's really a lot of work left to do to understand this system, right? And that seawater infiltration is something that's common enough to be worth the effort to understand. And so, to us, this includes working to distinguish brine and freshwater signatures better on the radar data, using that radiometric information to try and estimate total liquid water storage and salinity, sort of using all of that to have a more quantitative basis for thinking about the impacts of brine on ice rheology, hydrofracture, and freshwater aquifer formation. So I'll just close with a plug that I'm looking for PhD students to join my group at Cornell in fall 2024. So if you're a student and you're looking at this and it seems like really exciting questions to you, please get in touch with me. And likewise, for anyone else out there with questions, please feel free to reach out since I can't be there in person to answer. Thank you.
Riley, if you're watching online, thank you for that super interesting talk, and get well soon. Next, we'll have TJ Fudge tell us about late 20th century increase in Antarctic snow accumulation drives modest mitigation of sea level rise.
Great, thank you. David did a really nice job of setting this up, as did kind of Peter with motivation. And this front slide doesn't have either of my co-authors on it, but I think there's nothing that speaks to Antarctic accumulation like trying to dig out things from 3 years ago. So I wanted to start off with that. So this is really work led by Advik. He's just started his undergrad, so he worked with me a couple of years as a high school student. And the first task we gave him was to look at stuff at Herc Dome. He kind of quickly moved on from that, and he got really excited about trying to predict Antarctic climate using machine learning. So after trying to get me to understand what decision trees and random forests are and how they differ, and realizing that neither those techniques weren't really producing good results, we settled on trying to use the last millennium reanalysis, so a data assimilation technique really led by Greg Hakem at UW, and you've heard has been employed by quite a few folks in Eric Steig's group at UW as well. So, and this is all kind of motivated again by Brooks' work with Liz Thomas. And so kind of, looking at reconstructing Antarctic accumulation and using ice cores and techniques for spreading that information spatially to look back and kind of put modern changes in context. So what are our data sets? So we are using accumulation, annually resolved accumulation and water isotope records from around Antarctica. This map on the right is showing in light blue everything that was in the Thomas et al. Compilation. So we've also added in the water isotopes from the same page as 2K, kind of a series, and then we've added a few other ones kind of around that have become available since that was done. This graph on the left kind of shows the same thing that Peter was talking about, and why we kind of ended around 2000, and that the ice core records just drop off in number. So for our climate model prior, we're using a multi-model ensemble, and this is really where Olivia Truax, a postdoc with Eric Steig, has kind of come in to help. And our calibration period is the GISS temp 1950 to 1980. So it's very similar to what Gemma O'Connor was doing, and you saw some results of earlier, only we're looking at reconstructing Antarctic accumulation. I'll note we are doing this globally, though I'm only talking about Antarctica. So the way we decided to verify this was to look at the ERA5 record from 1980 to 2000, so post our kind of calibration period. And so we're going to be talking a lot about comparing with the Medley and Thomas 2019 paper, so that's what MT19 indicates. And so what you can see is that we get pretty good reconstruction skill in the Antarctic Peninsula and the West Antarctic ice sheet, less so in East Antarctica, although we still get significant results for the Antarctic ice sheet altogether. So if we just kind of quickly glance at the trends by sector, kind of the main takeaway that I want you guys to have here is this, that East Antarctica up there in C is pretty slight. Also note that there's a big scale bar change when you go to the Antarctic Peninsula. So, East Antarctica is kind of that, it's kind of a sleeping giant, doesn't get much accumulation, but does have a giant area. So what we kind of noticed when we look at the cumulative sea level mitigation, so integrating the increased snowfall from 1900 over the 19th century baseline, so 1800 to 1900, is that we so we do see that WAIS is kind of after about 1940 starting to contribute, but we actually have a bit of a decline in particularly East Antarctica dominating everything, but really an uncertainty that's really just around zero. Until we get into the late 20th century and kind of this after 1970, when things seem to start to accelerate and have kind of an Antarctic-wide signal. So if we kind of compare this cumulative sea level mitigation, what we can see is that we agree with an uncertainty with Brooke and Liz for WAIS. Also for the Antarctic Peninsula, we tend to be a little bit lower, and I think there's some reasons why the data assimilation technique might not be getting quite the magnitude right. But really the big disagreement here is East Antarctica, where I would argue this probably isn't that big of a surprise. We don't have a ton of skill there. It's hard to observe, it's hard to get ice cores, but a lot of what this comes down to is actually just what your 19th century baseline is. So if you're integrating above a value and you just have a little bit of a shift in that, then it's quite possible that you're kind of just integrating above the wrong number. And so that might be happening, but it might not. I would say that we're kind of in the level of uncertainty, but our uncertainty bounds for the 20th century mitigation of sea level in Antarctica should be greater overall than I think either of the individual analyses may be suggesting. And I want to make the point that it's not that I think that East Antarctica might not be mitigating sea level and might not into the future. One of the things that we're seeing is that the CMIP6 model accumulation to temperature sensitivity, so think how much more does it snow if you raise the temperature by a degree C, are relatively high throughout East Antarctica. That is something we find as well when we look at the LGM to Holocene temperature and accumulation in ice core data. So that spatial pattern actually agrees quite well. And it's actually pretty close to the Clausius-Clapeyron relationship in the interior, whereas around the edges, it seems to be more driven by atmospheric dynamics. So certainly with this analysis is cutting off in 2000, I think there's definitely the potential for there to be significant mitigation in East Antarctica going into the future. I will say that our results are suggesting that the dynamic loss that we have seen in the later part of the 20th century are not keeping pace with the ice dynamic losses. So here scale, roughly a factor of 2 lower. So it's unlikely it's going to be able to offset that, but it still could have some significant mitigation. So future progress for understanding this, I think one of the biggest challenges is just getting high quality records from East Antarctica. And really, you need them from at least like semi-coastal spots where you can resolve annual variations confidently in there. And then I think the other challenge is to bring these records into the modern and to be able to look at this up until 2020 or through time, and also blending the records together. So that ends that portion. I want to finish with my final minute with kind of announcement about the Herc Dome Ice Core project. So started with you with a photo from there, bringing it back. So basically here's kind of the timing for this project to get started. We've got the Intermediate Science Traverse, which is arriving in McMurdo on the vessels this season. That's getting commissioned in the following, with the idea that they're heading to Herc Dome in the 25-26 season to begin the drilling project. So that means first ice would return in 2026, with proposals to analyze the ice core timing kind of 2025. And I'll put up here what is my favorite Paul Cutler catchphrase, if you will, that, this will happen no sooner than. But I'm using it in a smaller font because I think there's increasing certainty about things. So, what's that? So with that, I'll end. Thank you.
Thank you, TJ. Next, I'll invite Radionovskaya Upwell during the 20th century from a paleo-oceanographic perspective. Take it away.
Thank you. Hi. Okay. So today I'm going to be presenting some paleoceanographic data. So I'm part of the Thor project, which is Thwaites Glacier Offshore Research Project. So I'd like to acknowledge all my collaborators without whom none of this work would be possible. Okay, so as part of Thwaites, there was 3 cruises during 2019, 2020, and 2021 field seasons. And the way that, the reason that we are interested in reconstructing past oceanographic temperatures is because warm circumpolar deep water comes in and upwells into the Amundsen Sea. And that causes oceanic forcing and melts the glaciers from underneath. So the way we are approaching this subject is by using marine sediment cores, and as you can see on this diagram, plenty of different types of data was collected as part of this cruises, including many marine sediment cores, which is what I'm going to be focusing on in this talk. Okay, and then how is I'm going to be using magnesium-calcium ratio from foraminifera as a proxy for temperature. So there's different types of foraminifera, which are unicellular shells that live in the ocean. We have planktonic foraminifera, which live in the surface ocean, and then 2 types of different benthic foraminifera, which live at the ocean bottom. And the ones we're specifically interested in is benthic and faunal ones that live just below the ocean sediment interface. And the reason this proxy works is because magnesium-calcium is magnesium is one of the ions that's substituted into calcite, which you can see on the panel C on the right-hand side. The green ions here are calcium, but magnesium occasionally gets substituted in. And this is an endothermic reaction according to this Van Hoff equation, so which means that it's temperature dependent. So if we reconstruct this ratio of magnesium to calcium ions within foraminifera, then we're able to deduce something about past ocean temperatures. But the problem is that it's very difficult to use this equilibrium thermodynamics equation to model the magnesium incorporation into foraminifera because it's a biological organism, so we have a lot of different vital effects. So in order to actually produce temperature estimates, we have to produce calibrations which are very species specific. So today I'm going to be presenting stuff from Chifferina angulata, which is the species that I've got highlighted here. And the reason this particular species is used is partially because it's present in enough amounts that we can actually reconstruct these temperatures. And also because it is genetically related to Euvidurina, which is the one next to it, and that's the one that's commonly used from elsewhere in the world oceans. So to begin with, in 2020, Elaine published this calibration, which was a new calibration specifically for the species so that we can actually deduce temperatures from the magnesium-calcium ratios we're getting. And as you can see, it basically fits really nicely this top panel over here with the Euvidurina estimates for the world oceans. And this calibration was done on core top studies from the map over there, and there's actually a really important piece of work because when we're dealing with such low temperatures, it's very hard to create these calibrations because we just don't have many data points, measurements, and we cannot reproduce these conditions very easily in the lab. Okay, so using these calibrations, we can produce different types of studies. So this is published work by CD. And what we can see is the Holocene reconstruction. So at the time of this publication, we did not yet have this calibration. And and we also did not have many magnesium-calcium data points. However, we can also use stable isotopes. And basically what CD showed really nicely in this paper is that you had more presence of the warm CDW during the early Holocene until around 9,000 years and actually a bit further on, during which we saw a lot of the melt of the Pine Island Glacier and other ice sheets in Amundsen Sea. And then during the rest of the Holocene, it was pretty stable and we saw cold Antarctic waters present. Okay, and this work was done from the two core sites I've got highlighted in green. So since then, so this is some unpublished work that I must acknowledge Elaine, who collected most of this data, and everyone else who's been working on this paper. But what we can see here, the bottom panel is the bottom water temperature reconstructions based on the magnesium calcium, which is panel B in the middle, and stable isotopes at the top. And what this work quite clearly shows is that actually we had this warm water present during the deglacial period at CDW when most of the glacier melt is thought to have occurred. And then during the Holocene, we had these colder waters present. So this work is a compilation of different core sites, which I've got highlighted here. So some from the inner shelf again, the ones from the previous slide, and then some from the outer shelf as well. And this is because we don't have enough forams continuously in any of the cores to actually produce one record. But it's interesting because then the panel in the middle is reconstructions of the sea ice extent based on various work with people in this room and others who cannot be here today. And basically it's thought that the current extent of ice sheets in Amundsen Sea was reached its current configuration by the beginning of the Holocene, which is what our magnesium-calcium temperatures actually agree very nicely with. Okay, so, and then I'm going to show some other preliminary data. So this will hopefully soon be published, so watch this space. Okay, and then to point out in this figure, time, this is now only the 20th century, so we've sort of migrated into more recent times. And time is now going from 1885 on the left-hand side to 2020 on the right-hand side. And this is some data from, again, one of these cores that's on the inner shelf. And we can see at the bottom here, I've got magnesium calcium plotted, and then isotopes and other proxy records. And I think if we highlight what's really interesting here is that you see this large increase in magnesium calcium and bottom water temperatures during the 1940s. Which, of course, there's been loads of suggestions that from the 1940s, that's when the recent ice sheet has been initiated again, and it has been linked to atmospheric changes in the large El Niño event, which the two top proxies show the sort of poleward shift and intensification of the southern hemisphere westerlies. So it's really cool that we get this change in magnesium calcium that's very obvious during these 1940s, but I guess there's also, with this particular data, there's a few caveats. So firstly, we see that the isotopes continue to increase as the dark blue record with I've got with the arrow pointing out, whether the magnesium calcium decreases again. So we sort of have to try and reconcile, because the magnesium calcium would then suggest that perhaps either CZW became colder again, or we had more influence of the Antarctic waters, which is not what we're seeing from the isotopes. However, in general, this still agrees quite well. And the other caveat we have with this data is we're having some issues. So this is based on a lead-210 age model, this particular graph that I'm presenting. But we've got some issues that we're trying to reconcile with some radiocarbon dates that we have for these core sites at the moment. So my project, or what I'm aiming to do, is basically to reconstruct more of the 20th century high-resolution records using the Thor Cruz material and different marine sediment cores, and basically to see whether we can get something like this, or from other cores and perhaps some other sites as well. So, and in terms of this record as well, so this is some recent reanalysis data. And I've just got the record that we were looking at, the magnesium calcium one in orange here, plotted as the bottom water temperature using the calibration that I showed earlier. But what is cool is that it actually agrees quite well with the ERA5 model reanalysis data. So this record, when we zoom in, especially into that later part, is actually in agreement with model reconstructions, which is also very interesting. Okay, and then, yeah, so like I mentioned, I've been doing quite a big survey of all these cores that are sort of plotted on this map. So some of them, well, the majority of them are from the Thor cruises. And a lot of these data points, for example, the triangles or the circles, they actually have a different types of cores, so multi-cores, casting cores, and piston cores. So there's several cores from most of these sites that I've been trying to look at. And yeah, and there is actually way more cores, around 130 altogether. Sediment cores were collected as part of the Thor project, but a lot of them don't have continuous foraminiferal records. So there's currently, these are the ones I've been trying to recreate these magnesium calcium records from. So, okay, cool. Well, that was a good timing.
Great, thank you to all of our presenters. We've heard some really interesting talks about both ocean and atmospheric drivers. So we'll invite all of the presenters to come back up for a panel discussion. And just a reminder that we invite particularly ECRs and new attendees to ask some questions, have your voice heard during this discussion, as well as everybody else in the room, and to, yeah, really try to think about tying some of these presentations together and what we can learn about, yeah, looking for connections between all of these projects. Looks like we've got a first question.
That was a great session. I have a question for TJ, and this was actually something I was going to ask David earlier. East Antarctica snowfall. It's hard. It will mitigate sea level. If our question at the WAIS Workshop revolves around sea level contributions, you know, how big of a push do we need to make on this constraint on East Antarctic surface mass balance? Because that's a hard question.
I definitely agree it's a hard question. I think another aspect of it is understanding the temperature out in East Antarctica. Just, I mean, not simply accumulation, but temperature and climate more generally. I don't think it becomes like the primary research question. I don't think it drives sea level in the same way that, you know, dynamic loss does. But I do think we should take advantage of opportunities to constrain it in many respects, because I think constraining that constrains the coastal climate that also drives sea level rise. So I think you've got an advantage to combine the two of them together.
Yeah, just related to that, I think, you know, if there is a sort of continent-wide or East Antarctic-wide need for shallow ice cores to constrain that more recent snow accumulation, it's ripe for the sort of Antarctic Rings international collaboration to make sure that we emphasize the importance of that and have ice core folks show up in that space, because it does sometimes on the face of it appear to be a very like airborne geophysics heavy initiative, but the international collaboration and actually having ground measurements is definitely a part of it.
Thanks, Peter. And yeah, it is really aerogeophysical heavy in its planning at the moment, and aerogeophysics needs fuel caches and landing sites and all sorts of things. That conversation ought to happen.
So I'll just kind of add to this. Brooke was telling me earlier that there's the last few years you've been able to see lots of increased accumulation in East Antarctica using ISAT-2. And I'm not familiar enough with that. I've got my head in million-year-old ice too often these days. But I think that that gives motivation towards understanding the increase that could occur, and something that we sometimes think about, which is the sensitivity of an increase in accumulation to an increase in temperature and how that'll play out. And I think it actually helps define the climate model performance as well.
I'm so sorry to jump in, but I'll be fast. I think a huge challenge for East Antarctica isn't the lack of cores, it's that the accumulation rate is so low, we don't get annual accumulation. Challenge interior. So a huge thing would be if some super smart high school now undergraduate student would take a lot of the volcanically derived, because there are records, they're just not annually resolved. How do we get those in? How do we get snow radar in? I mean, we're talking a lot about ice cores. Snow radar can give us a very long history. So I think there's information there. We just need to put the pieces together.
I just want to add on to that. I think it would be awesome, too, if we can get a better sense of the sensitivity of really extreme weather events that dump a ton of snowfall to changes in climate, because one of the biggest contributors to like the 2022 SMB anomaly in East Antarctica was this single heat wave atmospheric river event. So I think getting a better sense of those sensitivities to changes in climate would be awesome.
Yeah, I'll just add that obviously the surface mass balance number, whatever it is really important for sea level, but it's also important for climate modeling. So there's, for example, big differences between CSM1 and then CSM version 2 in their global climate sensitivity. CSM2 sensitivity is like 5 degrees Kelvin for a doubling of CO2. That's a full degree warmer than CSM1 was. And this surface mass balance, the cumulative surface mass balance is, it's an integrator of climate history. I think I heard someone yesterday say that the ice sheet is a low-pass filter of climate. So this integrated cumulative surface mass balance history is a real nice measure, I think, to compare to these models and figuring out not only are they getting the right number by the end of the 20th century, but are they getting the timing right? Because that has a lot to say about the history of not only greenhouse gases, but there's other things besides greenhouse gases like aerosols that are much more uncertain as to what they've done. And you know, that big number that CSM2 has for climate sensitivity has to do with aerosol cloud interactions, and we don't have a good handle on their history and how they work. So yeah, this surface mass balance is just a really neat kind of yardstick of the climate sensitivity.
Hi, thanks for some great talks. I have a question for Sophia, actually. With the records you have with the calcite precipitates of subglacial lake kind of flushing or flooding, do you have an idea of how the timescales of the flushing events that you've seen in those records compares to kind of active subglacial lake activity that we see now?
Yeah, so the timescales that we were observing within the subglacial precipitates appear to be centennial scale, so roughly 100 years. So the subglacial flushing events that we're observing in the modern are shorter than that. However, this could be due to like lake size. Like we might be looking at a different environment within the subglacial system. So.
Sort of related question. Did you did the Fourier analysis, but then you only showed two frequencies, centennial and millennial. Were there other frequencies in that Fourier analysis? If so, which?
So the strongest frequencies were the centennial and millennial. Yeah. With the centennial actually as the strongest.
A great series of talks there. Svetlana, I had a question about the data that CD produced back in his 2017 paper and showing a strong CDW signal in the early part of the Holocene. And I'm wondering, have the temperatures been reconstructed for that entire Holocene interval?
Sorry, you're wondering about the temperatures for the Holocene?
Right, yeah.
Yeah, so the second plot I showed with the paper and prep, so that for the Holocene section, that was the same cores, but actually with loads of magnesium calcium measurements on them.
Okay.
Which,
well, I missed that then. Can you remind us what the temperatures were?
Yeah, so that mainly showed basically a change in temperature transitions sort of right at the start of the Holocene, so from warmer during deglaciation onto the colder during the Holocene from around 10,000 years or so. So yes, there's like a little bit of a difference in the time transition when it happened between CD's paper and the unpublished record.
The timing of the presence of CDW, it was earlier or later?
In CD's paper, it was until later, because he suggested it was still there in the beginning of the Holocene, whether the other plot I showed was, it was gone by around 10,000 years or so. So, but I can show you again later.
Yeah, I'd like to see it. Yeah, sorry, I missed it.
Yeah,
but
no
what were the maximum temperatures you were getting?
Well, so I suppose this is tricky because it depends with the calibration. So we did a few sort of magnesium calcium corrections with manganese and stuff. So it depends. But the plot I showed, so that actually was realistic temperatures within the sort of realistic realm. So I think we got up to maybe 1.5. I'd have to double check. But yeah,
right.
so
let's catch up,
I suppose, yeah, so it's sort of, but I think regardless of any of the sort of corrections that we applied or things we did with the calibration, actually the transition is so strong between the colder and the warmer temperatures that it's definitely there at the onset of the Holocene.
Yeah, super exciting record. Yeah, thanks.
Cool.
So I also have a question to Svetlana. So one way that one could explain why Sophia's records show, a kind of more active subglacial water activity is incursions of, and that happens during the warm periods, AIMS, is that you would have incursions of CDW during these warm periods in the past, kind of destabilizing grounding lines. Is that record, magnesium calcite record, does it cover only since LGM till now, or is it can we go back in time to 120,000 years ago and compare it to Sophia's records?
So I think the one we currently have is only to that 20,000 years, so it's like around 19,000 or so actually, so that doesn't even quite reach the LGM. But maybe in the future if we keep drilling, I don't know, to be honest. I think it's very difficult to get cores where it's high enough resolution as well that we can get down to that.
But there's no physical reason, like the method should work back in time, yeah?
In theory, magnesium, calcium, yes, we can apply it throughout the world oceans, and it has been applied further back in time, but I think here as well, because we don't have many cores where we have enough foraminifera, because you need a certain amount of the same species to actually be able to generate these measurements. So I think that's our main constraint here, is actually finding cores with enough starting material to produce the analysis.
Okay, thank you.
So.
Just a response to the last question. I mean, if you show us where the core, the shelf core, where there's latent interglacial sediment is, we'll point Sveta at it.
Yes, I'm happy to do some analysis if you have forams.
Any last questions before we head? I think the next thing is a break. Am I right about that? Yeah. Okay, well, let's give last applause to our speakers, and then we'll head for a break.